Welcome to the Rutgers Experimental Math Seminar. Today's is the last talk in this semester given by Professor James Davenport, the computer algebra pioneer. We'll talk about complexity. Thank you. As usual, you're welcome to ask any questions. Unmute yourself and then mute yourself back. Thank you.
Right.
James, go ahead.
Okay. Right, thank you. Okay, so I'm going to talk about examples in mathematical sciences and how they might make us slightly rethink complexity theory and so on. And some of this is in a slightly old archive paper, which I really ought to update, especially if you ask me some really good questions. That will force me to update it even better. So thanks. Whoops. So I'm going to talk a bit about data citation, talk about collections in pure maths, and I'm extremely grateful that Neil has joined us here. Important test suites in SAT and SMT, the lack of proper test suites elsewhere, then talk about complexity theory and also perhaps its weaknesses. So data citation. We're all very used, of course, to citing papers. We all teach our research students, indeed, in many universities, we even teach the undergraduates how to cite papers. Data citation is much more of a mess in practice. And indeed, only 1% of the data sets in Zenodo, which is the EU's data repository, are cited. And indeed, 98.5% of those are self-citations. So other citations are rarity inside a rarity. It's also very poorly harvested, unlike citations of papers. So they looked at 3 different harvesters and drew the Venn diagrams. And the old trick of fishing, throwing the fish back and fishing again would take there something like 40,000 to 24,000 to 20,000 cited data sets waiting to be harvested. So that's not very good. It's still some uncertainty, and even last year there are more proposals way to do it. And people's answer to this typically is they cite a paper. You know, it's always the case you have to write a paper about your data because that way it'll get cited. Indeed, Stephen Watts has urged me to update that archive paper and write a bit more about this side of things and how to write a paper about data. So there are some important databases for mathematics. And obviously, the classic one is the online encyclopedia of integer sequences.
Thank you.
No, absolutely true. But it spent a long time at a personal website, which these days is not considered recommended. It is now at an official website, and it has enough momentum behind itself. But I do quote this as a warning because people very often do leave data on their personal websites, and they disappear. And if you're lucky, the internet, the Wayback Machine has them, and quite often it doesn't, and so on. So we do need to look after where we keep our data. And I'm really pleased to see that Neil did that with his vital database. There is indeed a recommended citation, but I must say you have to search the website quite hard to find it.
James, I was just about to write to you to say that that's really out of date. There's a much more recent citation recommended. I'll send you an email. I don't know if it's too late to change it in your article, but because I'm no longer the editor-in-chief. I'm the chairman these days.
Oh, right, yes. So someone else does the work. Excellent, yes. But yeah, okay. But one point I'll make is it took me quite a bit of finding on the web. I wrote this last year, so it took me quite a bit of time to search on the website to find it. I knew there must be one somewhere, but at the time when I looked, it wasn't terribly prominent. I'll look again. Another classic example is the classification of finite simple groups. It has been done, and that's actually quite small and is well known. The transitive groups acting on endpoints. The first big data set was done by Butler and Mackay. Then it's moved forward over the years. These are in GAP and Magma, except for at least for GAP, I don't know about Magma, n equals 32 isn't in the default build. It's bigger than the whole of the rest of the default build put together. So you have to ask for it. They're really great if that's what you want. And there are times in my research when I have wanted these, they're a really great resource. But again, it's not clear how to cite them. Do you say for gap group, gap transfer library? I'm really not sure. It's not obvious. There are other libraries as well, such as primitive groups and so on, in gap and other systems and so on. But in some sense, group theory is easy. For a given n, there are a finite number of groups of any particular property, and you just have to list them. Just, of course, not as easy as it sounds, because you've got to list them non-isomorphically and so on and so forth. But yeah, it's a good example where there's been a lot of work on producing great resources. Okay, now let me switch to SAT solving, and you'll see why later. I think I know it's a bit soon. SAT solving is normally seen as solving a Boolean expression written in conjunctive normal form. So 3 SAT is you have a 3 literals per clause problem. So you've got three literals all together and another 3 and so on, where each literal is either a variable or it's negative. And we ask ourselves, is it satisfiable? I.e., can we assign true and false to the xi's? Maybe x1 is false, x2 is true, and so on, such that all these clauses are simultaneously true. 3 SAT is the quintessential NP complete problem, going back to Cook's thesis. 2 SAT is polynomial, and for k greater than 3, k SAT is polynomial transformable into 3 SAT. So in one sense, that describes, from a complexity point of view, the SAT world. In practice, we actually deal with SAT. We don't care how many things are all together. We don't insist to be homogeneous or anything else. Just a load of ands of ors. And let little n be the number of variables that actually occur. Typically, little n is of a similar size to capital N, the number of clauses. I'm being deliberately vague here when I say of a similar size. But clearly it can't be too big, and there's redundancy if it's too small. Despite being NP complete, nearly all the examples are easy. For over 20, Cooklin and Sintz in 2000 had a paper describing how they introduced SAT solving to the German automobile industry. And for the last 20 years, every time we've walked into a German car showroom and ordered a car, there's a SAT solver between you and the car actually being made. And no one objects if this process is NP hard, because it just gets NP complete, just gets done. It takes fractions of a second. Or indeed,
what does it do, James? I was, when I read your paper, I was wondering how does the SAT come into the sales room?
So you specify you want right-hand drive, and then it does all the logical deductions based on right-hand drive, and says what kind of steering wheel you get and what kind of transmission, and therefore these parts need to be ordered for it and so on.
Yeah, fair enough. Thank you. Yeah.
And you have and things like you have certain options, therefore you need a certain size of alternator, and you're having it shipped to the US, so it has these US based constraints and so on. Yes. So essentially it's converting your spec into the actual almost literally nuts and bolts of the car.
Yeah, very good.
Yeah. And so it's got millions of variables, but they're all pretty obvious. From this steering wheel we deduce this and so on. But yeah. But I say, so SAT problems being solved for real millions of times a year. Equally, very easily proved insoluble. I was talking to someone else in this industry who, in the software industry, you want it to be unsolvable, unsatisfiable, because satisfiable would indicate a bug, and his software house solves literally millions of SAT problems a week as they verify their software. And they all produce unsat. Indeed, it appears that even for random problems, there's a very sharp phase transition between SAT and unsat. And almost no problems are difficult. And in fact, there's actually a difficult research area, which is constructing difficult problems for SAT. And people actually publish papers in precisely that area.
Okay, but one thing is, Excuse me. What is solving unsat is fundamentally different than solving sat, right? Unsat.
Well, the answer is fundamentally different, yes, but in fact, the technologies seem to be, but there was a time when there were sat tracks, unsat tracks in the sat competition, but these days, I think it's just one track. So the solve will either produce sat or it will produce unsat, depending on the problem, of course.
Yeah,
So
the only way they're equivalently hard is if NP is equal to co-NP, because one is NP complete and one is co-NP complete.
Oh, in terms of complexity theory, yes. In terms of complexity theory, yes, I agree with you. But in terms of the actual software, just goes off and produces one or the other. Yes.
Okay.
You're right. I'm sorry. Yes, complexity. Yes, you're right. We need NP to be co-NP for them to be equivalent problems in complexity theory. Yep.
Okay.
Yeah. But as I say, people do actually try to produce problems that are difficult to prove, sat or unsat, which of course isn't something that complexity theory will tell you. Well, there are many applications of sat solving. For example, trying to find new ways of multiplying matrices being reduced for a sat solving problem. So we want, in some sense, we want to solve real problems, not just random problems. And what does that mean? Well, the sat community has come some way towards answering that. They have sat competitions. And they've been for the last almost 20 years. In the beginning, they had distinct tracks for different kinds of problems. That's been abandoned. And the methodology here is that the organizer accepts submissions from the contestants and others. And indeed, last year at least, you couldn't submit a sat solve unless you also submitted problems. Then the organizers produce a list of problems in a standard format. They set a time and memory limit. They have the hardware, and they see how many of the problems the submitted systems can solve on the contest hardware. So it's a pretty level playing field. Now, of course, sat is easy to certify. You just produce a set of values which satisfies it. Unsat is much harder, but they've started requiring proofs of unsat, initially for the unsat track, and now they've abandoned it, and everyone has to produce an unsat track. And indeed, some of the proofs have been over 100 gigabytes, but nevertheless, they've been proofs of unsat. And the general feeling is that these contests have really pushed the development of sat solvers, saying that sat solvers are getting roughly twice as fast every year. This isn't the only area of software this is true. In the area of linear programming, Bob Bixby has been collecting this information for many years, and he reckons that over the last 30 years, linear programming has improved by a factor of 1.8 a year. Whereas Moore's law tells us that chips get faster root 2 every year, because they double every 2 years according to Moore's law, which brings us, as Bix points out, to the fact that if you're doing linear programming, you're better off running today's software on 1990 hardware rather than running 1990 software on today's hardware. So software is more powerful than hardware in at least this example. And linear programming, of course, again, has a tremendous commercial market, and that's what's pushed the development of it in a measurable way. Although I said earlier we can reduce sat and k-sat to 3 sat, we shouldn't do this in practice. In fact, some solvers look for this reduction and undo it, because they'd rather have a fewer but longer clauses. A significant practical development in this area was the idea of 2-watch literals, which means that most of the time we don't even look at the whole clause. There's a good description here of it. In the worst case, it's no more efficient than the algorithm it replaced. But in practice, it's hundreds of times more efficient. There's an idea called not moving back, which doesn't look very great. It looks worth normally at most a factor of 2. In fact, it's a factor of 10. So that's just a description of the difference, as it were, between theory and practice. A particular point is that if implemented correctly, 2-watch literals is much more cache efficient. You don't actually keep the clauses in the cache most of the time. Ideas like this are essentially orthogonal to complexity theory as we know it. There is a life beyond sat called satisfiability modulo theories. We consider a theory T, which has some variables in it, going to go yj, and various statements in T with some function of some Boolean valued function of the y's, and we make a conjunctive normal form of these rather than just of the xi's. So the yj's might be real variables and the fi's might be inequalities or something. That's the theory I like to use. Other people have the theory of arrays and so on. And SMT is very much used in program verification. SAT and unsat problems are the same, except we're now asking, are there values of the theory variables, not just are there values of the xi's? And of course, if your theory is over the reals, there are uncounted many reals, so enumeration doesn't work, obviously. And again, the community runs SMT competitions with a separate track for each theory. There's a standard input format again. It's much harder to describe unsat here. We've been doing some work on unsat for the reals, but in general it's unsolved as to what a proof of unsat might be, which is a good research question. And again, there's been substantial progress in SMT solving. It's harder to measure, but it's probably similar to that of SAT solving is the impression I get. Again, very much pushed by the contests. So what about computer algebra? Well, obviously, group theory is part of computer algebra, but what about the sort of the polynomial end of computer algebra? Much traditional complexity theory is for dense polynomials and matrices, but real life is often about sparse ones. In general, many of the problems we talk about, particularly if we do a sparse encoding, have a bad worst case complexity. And though it doesn't actually admit it, well, computer algebra is actually in a very similar case to SAT solving. We want effective solvers for real problems. The question, of course, is then what does this mean? There's a problem of format. There's no real common standard. We do have open math, but it's not as widely supported as we would like. Contests, there aren't really any contests. Each author writing a paper shows that their software on their examples runs faster than everyone else, and well, they would do, wouldn't they? It's essentially there are no unbiased contests with an independent jury setting a set of problems. What I'm saying here, yes. And there isn't really an archive of them, and that will come up as I go through the various cases. So polynomial GCD, which was the hard problem of the 1960s, and then for dense polynomials, it was solved by people like Brown and Collins and so on. And for dense polynomials, it's solved. For sparse polynomials, it's NP hard, even for univariate sparse polynomials. It can still be quite challenging for multivariates. There's no standard database. Again, if I have a research student or MSc student doing a project in GCD, I have to say, well, go and read the papers and see what examples they used. And quite often, especially these days, people have larger examples, you've got to ask the authors, and they tell you they've forgotten it, or they send you a PDF or a file in some format you can't read, and so on. Yeah. But people chuckle with that one, yes. Verification is an interesting challenge here. You can check easy enough what you have is a common divisor, but in fact, Placed also proved that verifying that it was the greatest was again NP hard, because that's the same thing as saying that once you divide it out, the two are co-prime. Now, this is interesting because the NP hardness results of Placed rely on encoding a SAT formula W as a polynomial which vanishes at the roots of unity, where each prime here corresponds to one of the xi's here, and so you can check which ones it vanishes at. But there are also some blow-up results. Andre Schinzel had a lovely one here. You take a 2-term polynomial and a 4-term polynomial, and then depending on your primes, you've got any number of terms you want in the GCD. With Jacques Carrette, I asked, are cyclotomics x to the n minus 1 essentially the only cause of problems? And particularly, we then went on to ask, so suppose we insisted that, whoops, that shouldn't be complex numbers, C, sorry. We insisted that you set, if a polynomial was cyclotomic, you said so. If it was a product of cyclotomics or has cyclotomic factors, you said so. then this would be a statement about the GCD of cyclotomics, and that's a trivial piece of cyclotomic algebra, because you've said they're cyclotomics. And it's still open as to whether that would actually, I won't say solve, because obviously you can't solve an NP hardness problem. It will banish the NP hardness problem. Let me use that word. But these are still open problems. Polynomial factorization, again, a major challenge. The standard algorithm, Hensel lifting, has exponential worst case behavior, as in Swinton-Dyer's letter to Burleycamp. Collins, however, conjectured that this had polynomial average time, in a sense I'll have to talk about later. We now know it's polynomial time for dense encodings from Lenstra-Lobash, but a very bad exponent. Of course, if you factor it, there's exponentially larger output for sparse encodings. And I believe, or I've not seen it actually proved, that it's NP hard even in terms of the output size for sparse encoded polynomials. Again, verification is a challenge. You can obviously check the results of the factorization, but checking completeness, i.e. that the factor is reducible, is in the worst case, I emphasize that, as hard as the original problem. But the problem with this is that with probability 1, a random polynomial is irreducible. So I've got a very nice Monte Carlo algorithm that just says irreducible all the time, and it's wrong with probability 0. It's not very helpful, but it's there is the point. And Collins's definition of average time was actually quite subtle. It's average time overall partitions of polynomials modulo p, refining partitions over the integers. It can't just be average over polynomials, because the running time is small, because they're always irreducible. We point out some time ago, but you get difficult problems from factoring over algebraic number fields, and that happens quite often in real life. So the difficult examples do crop up surprisingly often. So we actually have, if you actually implement factorizations, you have an engineering task, as it were, of switching between the exponential but generally quick algorithms and the slow but guaranteed polynomial algorithms. And the trick is to define your switching point such that you do actually do the quick ones quickly, but you do the slow ones in polynomial time. Again, there's no standard database, same warning as before. So what constitutes a good benchmark for such tasks? Moving on, Grosvenor bases. Again, doubly exponential with respect to number of variables. And that's true even if it's a prime ideal, which is a result of Christophe, which I found quite surprising. There is a collection of examples here, there's a European project which I was involved in, which actually collected a set of examples, and that's there. Unfortunately, it's very old and it's completely static, but it's a PDF. And indeed, being a PDF, it's a pain in the neck to input to anything else. Again, the point is, the generic case is not interesting. There's a result, there's a shape lemma, which says that generically it'll be equivalent to a triangular matrix, and it won't be an interesting Grosvenor base. Again, there's no concept of answer here. It's not even clear what certificate might mean in practice to prove that what you've got out is a Grosvenor base of what you started with. Real algebraic geometry, cylindrical algebraic decomposition, which is my current research area. Again, that's doubly exponential with respect to number of variables. There's a collection produced by my former research student. Again, it's not as old, but it's still somewhat old and completely static. Our current research project is looking at updating that. There's still issues of long-term conservation and so on, and we're not as famous or as valuable as Neil's work to have our own website yet, but there are issues of long-term conservation, which Neil has addressed brilliantly in his own project, and the rest of us should emulate. Our current format is in plain text and Maple and QuepCAD inputs, which at least gives you a range of things, and they are actually machine readable, even if you haven't got any of those software systems, you can look up a parser because it's sensibly written. Again, but in general, there's no concept of unsat, but there was a paper at SINASC which got somewhere towards it. It's still not quite clear what a certificate might mean. However, let A be the number. So talk about quantifier elimination. So you've got for all there exists, let A be the number of alternations of quantifiers. So the example of Brown and Davenport, which showed double exponential, had as much alternation as possible. There are n quantifiers, and they alternated exists, all, etc. There are unimplemented algorithms of quantifier elimination, which are provably d to the power of some polynomial in n, so it's singly exponential in n, where we don't actually know what the degree of that polynomial is, and doubly exponential only in a. And furthermore, there are implemented algorithms which might have a similar complexity. That's not been proved. So we have things that are proven and things that can be run, and never the twain shall meet yet. The world of software, or indeed cyber physical systems, where you're simulating computer control of a real device, tends to produce examples with a equals 0. So there's no alternation. The problem is, does there exist a geometry which is bad, where bad is some enormous CNF in statements about the various variables, and geometry is probably a lot of variables. There's no alternation here. We just want to know, or we rather want to prove that this is not true. We want to prove there is no bad geometry, typically. So looking at problems with A0 is probably a good idea. Indeed, a good question is, are there any natural examples of quantifier elimination with A non-trivial? I can think of quite a few with A equals 1, but then it begins to run out. So that's a good question. I don't want to say something about integration because I morally have to. The complexity is essentially unknown. As an interesting question here is the niceness of the output, because there can be lots of alternative formulations of the same output. Pure mathematics here produces some large databases, Grajtin and Rijik, and several other integral tables. Probably the best database actually these days is in Jeffrey and Rich. And algorithm-based software, such as my own PhD thesis, internally has a proof of unsat. But I don't know any software that actually expresses that. You sort of have to sort of trace the inner workings and work out the deductions by hand, which is not very satisfactory. It's a bit of a weakness at the moment, I think. Anyway, that's integration. Where I say it's rather different because we asked the question, how nice is the output? Which is an interesting question, but a rather different one. So I said earlier I talk about complexity theory, and I believe that there shouldn't be black swans. Why do I say that? That's actually the title of the Amundsen and Lutz paper, Average Case Complexity about the Black Swans. And they have this interesting definition. So by without black swans, they mean without an exponentially rare family. But that exponentially rare family is worse than exponentially bad. So if you had it, it would swamp everything else. It would dominate the average case complexity, even though it's exponentially rare. So their definition basically says, we say it's got a weak expectation if the expectation is bounded by f of k, if you exclude the things in an exponentially rare set. And of course, you need a variable k tending to infinity and so on. And we need to ensure that the constants are independent of k and so on. It's one of those slightly messy definitions, but the idea is that we exclude exponentially rare families. And they go on to prove 3 quite common items which actually have a decent weak complexity despite having very poor or indeed infinite complexity. So one of them is condition numbers, which includes condition numbers of matrices, a special case, condition numbers for conic optimization, and running time of power iteration for eigenvectors. And all of these have very bad, indeed, in general, infinite complexity, but only on an exponentially rare set. And that's the point of their definition. and it's quite an interesting paper in my view. So now come some guesses. These are, I don't even want to dignify these with the phrase conjecture, guesses. The first guess is that Grosvenor-based computation is weakly singling exponential in n. We have these examples which are doubly exponential. They're very contrived and in some sense quite fragile. And the guess would say that there's some small family of examples which are extremely rare. It needs to measure on set polynomial inputs or possibly measure on the ideals. And it's not quite clear how to do that and so on. So that's why it's not even a conjecture, it's a guess. You might need some further restrictions. Initially, I tried to do this, restricting it to radical ideals, but Chistov has a bad example, even in the case of radical ideals. And I have no idea how one might prove that, having looked at Chistov's example of sort of, in one sense, understand it, in another sense, fail to understand it in the sense that I can't prove that it's rare in some sense. That's a worry.
But can you prove it experimentally by doing lots of examples and finding the average?
Well, almost all Grosvenor bases are trivial. Yes, that's the point. So yeah, and in some sense, this would be, if I could prove it was I have to prove it's exponentially rare. I don't think you can verify exponential rareness computationally.
Yeah,
you can verify sort of linear rareness or something, but beyond that, I think we're outside the realm of experimental mathematics in that way.
Yeah.
Not in all ways. There's a question. The next question is, what happens if you vary these worst case examples? It turns out they're all very fragile. Almost any variation of them is actually quite well behaved, unless you vary it in a very prescribed direction. And essentially, it's essentially the same example under an obvious transformation.
Interesting.
But yes, so experiment is good in that sense. The experiment tends to show that at least this example is not part of the wide family. That doesn't mean there isn't another one. That's the problem. But yeah, I mean, I'm not saying experimentation no good. I'm saying you can't prove exponential rareness by direct experimentation. And that's in some sense the problem in this area. One has an intuition in that when you experiment, you almost never find bad cases. But someone's gone off and proved there are some bad cases. And where is the middle ground? That's in some sense the question I'm asking. Thank you, Doran, for asking your question. Sometimes I'm saying, how do we get between, I know they're very rare, I know they're very bad cases because someone has proved one. I never come across one by accident. So where's the middle ground here?
Yeah, very delicate.
Yes, indeed. I say when I talk about polynomial factorization, we discovered that we did keep falling across the bad cases because every time you played around with algebraic number fields, you took norms to reduce them to polynomials, and those norms were nearly always badly behaved. So there we have a recipe for constructing lots and lots of bad examples. But here I don't. I just know a couple of bad examples and trivial variations on them. So that's why I'm guessing. Yeah, my guess basically is that I only know a very small number of examples, which of course is a long way from being a proof. Similarly, I'm guessing that the real quantifier elimination is weakly singling exponential in the number of variables for any ratio of alternations to variables. Obviously, if I've got no alternations, ratio 0. I can't have more alternations than quantifiers, so it's somewhere between 0 and 1. I'm guessing that for any such ratio, it's weakly singling exponential in n, i.e. that the bad guys are exponentially rare. Here again, this is based essentially on the feeling that I know a couple of fairly fragile bad guys, and nothing else appears to be. But again, this is weaker. I'm less confident in this one than the previous one, which is pretty bad. Again, the question again is, I need to measure on inputs because we don't have the same idea as we do in the case of the basis. I don't have an abstract concept of an ideal that I can really use, because a cylindrical algebraic decomposition is not really an inherent concept in the same sense as an ideal is. So those are my guesses as to what we might be able to do at some point. I'm not holding my breath though, I'll be honest. So where do I think we should be going? Well, first, I think we need to be more inventive around complexity theory. Although I can't apply it directly, I do like the idea of weak complexity here, which says we can throw away the bad guys for either exponentially rare. Indeed, maybe even when it comes to NP hard problems, can we say something that the NP hard ones are rare? We have to be, of course, polynomially rare, and I don't know how to do that. Obvious statements are either trivial or false, or possibly both. But nevertheless, I think we need to be more inventive around complexity theory and be able to say things about common behavior. I believe the field really ought to invest in the sort of contests that have so simulated the SAT and SMT worlds. It requires a much larger database of relevant problems than we currently have. They need to be properly curated, and but I think the SAT and SMT communities have done a much better job of that than we in computer algebra have. And of course, the other point is that technology, wikis or GitHub or something, has greatly advanced since the days when the POSO project collected polynomials by email and so on. And it should be comparatively easier to build at least a database of examples. I mean, OES has a wonderful set of tools around it, which I believe have taken some time to develop. Is that right, Neil? Yeah.
Turn on my microphone. Absolutely. Yeah, we've been doing this for a long time.
Exactly. But equally, of course, OEIS shows you where you can get to if you start a long time ago and start working.
55 years. Yeah.
Yes. So it's something we should be looking up to and saying, as a community, we can't get there overnight, but do we want to get there at all? And congratulations on your efforts. And if we did these, we'd allow much better benchmarking technology, and the benchmarking technology and the construction of things that work well on average is much more advanced in the SAT SMT world than it is in computer algebra, where essentially people produce papers with half a dozen examples and say mine is 10 times faster than everyone else on these half dozen examples. And so that's the example. That's a paper describing how benchmarking works in that field aimed at the computer algebra field. Okay, so that's what I want to say. I've finished, I think, slightly early, Doron, but I'm very open to questions.
Well, thanks for a great talk. Please unmute yourself and thank James. And we have quite some time for questions in this intriguing thing. I have a quick question / comment. So implicitly, is it a criticism of mainstream complexity theory that it's very nice theory, but it's not that relevant to the real world?
It doesn't answer all the real world's questions, and NP hardness is a good one. It's a good example. It's a very important definition. I'm not going to knock it, but in some sense, within that, there are problems that are NP hard but almost always easy, like SAT. And there are problems that are NP hard and generally nearly always hard, like traveling salesman. And somehow we can't describe that difference in anything like as nice a way. So what I'm trying, I'm not complexity is great, but it is not perfect, and in some sense, I don't think it's complete, and that's why I quite like the weak complexity theory of Amundsen and Lutz. Not that I can use it myself directly, but at least it tells us there's more than the classical complexity theory, and so I think my first bullet point here is that we actually need to be more inventive.
So the notion of weak complexity, weak average complexity, is it a new concept? It's new to you?
The weak asymptotic goes back to the Amundsen and Lutz paper, 2017. So it's very inventive. That when I came across that opened my eyes to the idea that there could be a formal definition which let you say, except for a set of exponentially small measure, because we can't just say sets of measure 0, but this formulation, while a bit cumbersome, you know, it is as it were the right one. It does as they say, this is all their work here. It does encapsulate some common cases where things have a very bad worst case, but actually that never happens. And you know, people use power iteration on Hermitian matrices all the time.
Yeah.
Yes.
Yeah, it's very natural.
Yeah.
Any other questions or comments for James?
Yes, I was. This is Victor. I was thinking that one of the practical defects are that we look at, for example, if you look at random 3-set, I mean, this doesn't really have any resemblance to real SAT problems. This is why the SAT they have different tracks for industrial. So you could think of it in a maybe a more abstract way, is that what we're really interested in is we're generating problems that are in some big parameter space, but we don't know what the parameters are. And when we conflate them into something, we sort of wash out the interesting, you know, sets of parameters. And I know, at least in the theoretical side, I know parameterized complexity has been trying to do something along those lines, where basically they show that if you have a problem, some problem that comes from that class, that it's polynomial, but the constant might be exponential or even worse in terms of the parameters. And that's, you sort of alluded to that informally, I think, but. But
yes, you're absolutely right, Victor. I should probably have said something about parameterized complexity, but I haven't been able to apply that to my sort of computer algebra yet, which is probably my fault. I just at the moment can't see it. But yeah, you're absolutely right. It is another direction in which complexity theory is being more inventive. Yeah, I'll say that. Yes.
Yes. Yeah, I will say I tried reading some of these papers. They're not easy reading, that's for sure.
Yes.
More questions and or comments?
I have a question, James. So this reference AL17.
Yes.
Can we see the reference? Oh yeah.
Yes.
Okay, thank you.
I don't know, Dawn, do you collect the slides of speakers? If you do, I can send them to you.
Oh, I believe Doran will post the slides, right?
Yeah, we collect them.
Okay.
Yeah, okay. Yep.
Thank you, James.
Yes.
More questions for James?
Well, I had one question, but that's like you probably answered it. I just was not very attentive. So these difficult problems, like in like Gröbner basis or cylindrical decomposition. So the nature of hardness comes from what? From intermediate expressions, well, or from something else? Like what is? Like input is small, output is probably also small. So where is then hardness hidden? like in cylindrical decomposition.
Yes, so the examples we know for cylindrical decomposition, the hardness is hidden in the number of alternations. And essentially what happens is conversion between conjunctive normal form and disjunctive normal form, you can get an exponential blow up.
Yeah, well, that's intermediate expressions, well, right?
Yes, and you can get that every time your quantifiers alternate, and that's essentially how the Davenport-Heinz example works.
So yeah, I was just curious because in our business of summation, I introduced this. There is a non-essential dependency of running time on parameter, or essential one, and essential it is feature of a problem, and
yeah.
Non-essential is feature of an algorithm you use.
Yeah.
So this in cylindrical decomposition, this is feature of algorithm you use to solve the problem, or this is just nature of the problem.
Okay, so because the nature of the problem has it doubly exponentially the number of alternations.
Okay.
And that's the Brown-Davenport lower bound. But that lower bound is essentially your terminology in A.
Mm-hmm.
The fact that current algorithms are all doubly exponential in N, but that's current algorithms. That's not necessarily essential.
Okay.
So yes, but of course A can be as big as N, but nevertheless the essential dependence is on A, not on N.
Yeah. Okay. Okay. Thank you.
Thanks so much.
Why it's important to see that A equals 0 is a common case.
Mm-hmm.
Because that tells us that the essential dependence and the accidental dependence are very different.
Mm-hmm.
So we need better algorithms.
Thank you, James, for a great talk. This ends the formal part of the talk. Thanks, James, again.
Thank you. Great talk.
Robert, please stop recording. People are welcome to stay for a few minutes if they have informal questions.